This conference will now be recorded.
Hey everyone, thank you for joining us again today. I'm your host, Shayla Redmond, and welcome to another Project Possum's Astronaut Mentality series. Yesterday's topic was fueling the fire, nutrition for space, and quarantine. You learned possible future of sustainable food on Earth could be freeze-dried food, but just don't add too much water. Yesterday's challenge was could you eat like a Martian? Why or why not? What food habits have you noticed while in self isolation? And I have a comment from Nicole Burke, who joined us yesterday. She was saying that she heard many farmers are having to waste food because they cannot distribute it. She was thinking that the need for more efficient ways to get fresh food distributed, and that the freeze-dried food should be something to think about. So that's definitely a great comment and a great thought from Nicole Burke. And don't forget that the previous webinars, you can always go back and listen to them and even answer some of the challenges. Just you can put hashtag Possum Astronaut Mentality on any platform that you choose. So today, if there's anything else, Shauna, do you have anything else from social media?
Not from social media, but once you're done, I do have a few questions from previous webinars that I can get to.
Okay, I'm done. After that, we'll just introduce the moderator.
All right, so first things first, thank you everyone for coming and joining us again today. From yesterday, we had the amazing Dr. Cyan Proctor with her challenge and competitions related to nutrition in quarantine. So for those of you who may remember, Cyan is running a competition called Meals for Mars. So submit your favorite recipe before April 30th, and you get a chance to win a copy of her cookbook. So Cyan, I'll let you drop that in the chat. Next up, from our webinar on risk management, operational environments, as well as critical decision making in tight spots, one of our very own audience members, Jan Zimmerman from Germany, put in some input about how his company handles risk management with the 5W method, as well as the STOP method. So I just thought I would share that. So the 5W method can essentially be summarized as why, and ask why something happened until you get to the root cause. And then the STOP method can be translated into substitute, I remove the source of danger. If that doesn't work, find a technical solution. If that doesn't work, have an organizational strategy. And finally, the P stands for personal measures or PPEs. So it's a very interesting method. Thank you for sending that handout along, Jan. Last question from a previous webinar, Camille Henry from France had asked about ESA cave training and whether any of the other astronauts engage in that. So we talked about that, how the European Space Agency astronauts work on ESA caves and in small groups in a confined space in a rather high-risk operational environment. They do some team building, but it's actually quite an international venture. So the Canadian astronauts, Josh and Jenny, have been part of that. NASA astronauts do partake in that. So as a follow-up, it is actually the way the other astronauts outside of ESA partake in that is by participating in ESA caves. So great question there. That's about it for questions. As always, drop your questions into the chat. Let us know where you're dialing in from this morning. We like to see our international audience. And without further ado, I'm going to turn it over to our moderator, returning us from yesterday's panel to moderate today, the one, the only Anthony Navarro.
Thank you, Shauna. I'm excited to talk about today's panel. We're going over underwater analogs, and I'd like to introduce both of our keynote speakers really quick. We've got Matt Harashimchuk. Sorry if I messed that up. Matt is a Chief Aerospace Systems Engineer at Astrotech and Director of Flight Crew Operations at Analog Astronaut Training Center. He's an advisory board member for astronautics and aerospace at India Research Center and a former engineer at the European Space Agency. He holds a Bachelor's of Science in Software Engineering and a Master's of Science in Aerospace and Aeronautics from the Polish Air Force Academy. We've also got Stephen Shamar, and Stephen is an Eagle Scout alumni, Order of the Aero Vigil Honor, Phi Kappa Tau Brother, Pretty Lights Illuminator, Explorer Club member, Space Ambassador, and Protein Industries founder. He holds an Evolutionary Anthropology Bachelor's of Science and an Evolutionary Medicine Graduate Certificate and Geographic Information Science and Technology Master's of Science. Matt, I will hand it off over to you to kick off our keynote session.
Okay, thank you very much. So hello everybody, my name is Matt Harastymczuk. It's hard even for Polish people, and I would like to present you with the topic of underwater analogs. I'm in the business of analogs since 2016, which I started from building from scratch a habitat in Poland. The first version and then the second version, in which Sian Proctor was also in our missions for 2 weeks, so that's also very nice. Today, I'm with the underwater analogs, which is personal interest of me because I am also building underwater habitat, but this is a long time project. So let's start with the presentation. So if you are in the topic of space analogs underwater, we have like 4 main common topics in which the water is used by the astronauts or by the crews for training, EVA training. So for the people, here you have a picture from Hydrolab, which is the Russian neutral buoyancy facility, with the astronauts in the Sokol spacesuits, in the Orlan spacesuits, which are training outside of the ISS mock-up. Then you have also post-landing and water survival training courses, which Jason provides in Groton, which is a very nice course, and I really recommend this course for everyone. You have isolation studies inside of the habitats, because one of the main ideas behind the habitats is also about the isolation from the outside world, from the conditions and so on. Because when you are diving, and especially if we are talking about the saturation diving, which is by the medical community, when you are a saturated diver, then you are spending more than 1 day under the water. When your tissues are fully saturated with the nitrogen, and then you cannot emerge to the surface in one take. Then you can also use the analogs, and especially you can use underwater for testing bed, for testing tools like scoops, pickers, and some fancy carts. And as you can see in the background, there's an astronaut with a scoop, but next to him, on the right side, there's a small cart. And this cart is designed by my colleague of mine, which with her I spent around a month in isolation in our habitat. And right now she's working for European Astronaut Center, and she designed this cart, and they tested this during the NEMOS 23 last year when the Samantha Cristoforetti was the head and commander. Okay, so when we are speaking about the space analogs, I want to go into details. There's a couple of neutral buoyancy facilities or laboratories in the world. In the United States, you have 2. One there's in Cologne, one in Russia, and one in China. This is the main. There was also one in Japan, but it's not currently used after the earthquake anymore. And we have one and only unique Aquarius habitat, which is the very nice topic for the future. So this is a picture from astronauts. They are using MESIS trainings, the MESIS suits, which are the evolution of the ACES suit. Those suits haven't flown, and they were supposed to be in the Orion project, where they wanted to go for the astronauts, to capture the astronauts and then the asteroids, and the astronauts. They were thinking about merging the IVA and EVA training suits in one. And after this training course, the fun fact is the astronauts, after this training session, they said that striking with a rock hammer next to the very thin plastic visor, it was a bit disturbing, and they were really afraid. Maybe not afraid, but they were like not very happy about this thing that they have very sharp objects next to their visors. In the European Space Agency, they don't have full-fledged neutral buoyancy facility, which is the largest swimming pool in the Earth, and so they have a little bit. They have smaller pool in which they do pre-familiarization with the EVAs. So what they are doing, they are using not EMU spacesuits, but they are using mock-ups. So they try to have mask with the similar field of view, but also they are using the regular gloves, and they have their belts with the same tools that they use in the EVAs. So the idea behind this is to have neutrally buoyant astronauts, which do behave like the same like on NBL, because NBL is heavy. They have very heavy workload, and the European Space Agency cannot send the astronauts straight to the NBL for training the full-fledged EVAs. So they are doing pre-familiarization in the European Space Astronaut Center in Cologne, and then after training the astronauts to a certain degree, they are sending them to the US, and they receive very good marks from the astronauts EVA trainers. So Thomas Posquet last year, he did training course with the Nitico Research Limited company, which they developed a couple of devices, one suit and two submarines, small submarines, which are used in the analogs for quite a long time. And in the NEMO missions, they haven't tried this at the NEMO. They did try this training suit at the different occasion, but during the NEMO, they are testing the vehicle, which is also their design. And there are very nice pictures of, for example, Chris Hadfield, who is like flying around in the submarine and testing. But European Space Agency, or COMEX, which is the company which has been specializing in underwater equipment for like 50 years, they are also trying to do and to create a spacesuit, maybe not next generation spacesuit, but at least some remarks for the European spacesuit, which is going to be underwater. As you can see, this spacesuit is a bit different because it's not having like full enclosure. So what you have is a diver inside of the mask and with the scuba gear and regulator, which is breathing. And this is all for the safety reason, because they do not have the fully fledged life support system like they have on the exosuits, which the exosuits the exosuit suit can go for up 1,000 feet, and they are having a next generation suit which will be available to achieve 2,000 feet, and they can stay underwater for 50 hours, okay, 50 hours in the suit, because they have the carbon scrubbers and scrubbers and all the systems for supporting the life inside of this small vessel for such a long time. As I mentioned, the same company also developed two submarines, small personal for use. One is for one person and two for two, and those submarines was in the missions. So as a test bed, the underwater analogs are used for testing not only equipment but also procedures and for example documentation of the minerals and places where the minerals are stored, and also so the astronauts can evaluate the efficiency of the procedures, easy of use, and they also can train on the equipment, which is in most cases proof of concept devices, but also on the TRL, higher on the TRL levels. Underwater analogs are parts of the isolation, and during the NEMO 21, I suppose, there was a HoloLens in which they tried to use. So during the NEMO 16, they used MobiPV, which is something similar to Google Glass. And this MobiPV device was first started in European Astronaut Center. Then they tested in NEMO. Andreas Mogensen was using this in NEMO, and then Andreas Mogensen also used this on the ISS on his flight when he was in the space. that was one of the first approaches on having just-in-time delivery of the training materials for the astronauts for the procedure viewers. MobiPV stands for Mobile Procedure Viewer. But also, right now, HoloLens is more capable platform, and right now they are using and trying to use HoloLens for supporting astronauts, for example, during the EVA, for showing map of the ISS and where they're located, and showing, of course, procedures how to mount the equipment and so on. But underwater analogs can be also a platform for testing human-robotic interaction. And this is also very important, especially because right now there's a question, human or robotic interaction. And I don't believe in this division. And I do believe in that the future exploration of Moon and Mars will be human and robots. So, of course, we need to learn how to interact with each other and how to work with our interfaces, especially because I personally broke one rover when there was a gripper, and the gripper was just having like a claw, and I was trying to pick the rock, and unfortunately I had a half a second lag, and I wasn't able to match in the same moment to release the force on the gripper, and unfortunately I broke the arm of the gripper, which wasn't very nice, because then we didn't have the spare parts in our simulation, and that was the end of the using rover, because the guys who lent us rover they were very mad about us. But the same thing can apply, the same thing can happen on the Moon or Mars, and that's because I didn't have haptic feedback. Haptic feedback is one part, but you also have to interact, and you have to also learn how to interact with the devices, and especially if you have robotic interfaces, which you cannot sense how strong are you, for example, trying to apply the force on rock or something like that. But you can also evaluate the human performance underwater. And there are a couple of tests, like, for example, during Nemo 23, Jessica Watkins was doing the dexterity and evaluation with the peg boards. This is a standard test for the astronauts after they came back from the space flight, when they measure and they also check against their performance before flight, and also that they are using the same thing during the astronaut selection, when they put the selectee, or the person who is going to applicate for the astronaut, they put on a spinning wheel. They're trying to rotate him, and then to check the dexterity and how the rotation influence on the person, on the vestibular system in your head. But also you can have cognitive tests, and especially in the underwater confined places, like isolation in a habitat. This is the first thing, but also remember that you are underwater without any possibility to emerge quickly, and the decompression inside of the habitat is around 18 hours when you are safe to go to emerge from the sea. So you cannot go simply, because you will have the bends, the DCS syndrome. So you cannot do that. And also you can test and to measure the performance of using, for example, 3D printed panels or different stuff. One of the analog, the best places to train astronauts, which is typically not geologists or not, they are coming from different backgrounds. In geological, of course, you go with them to the analogs, like Lanzarote, like Utah Desert or F-Mars. They have a really nice analog in the Devon Island, and some other places like high seas habitats. But you try to put them in the isolation or in the similar condition with the similar geological features that they have on the Moon or Mars and so on. But underwater, you have completely different environment, and you have different aspects of taking sampling and sampling, because you have drag, you have some other stuff.
Hey Matt, just wanted to let you know we're about at time, so if you want to wrap up real quick, and we'll switch over to Stephen.
That's right. So one of the last thing I wanted to state is that the most important thing is to train contingency situations. Underwater testing, and this is where European Space Agency came up with the idea of LISA, which is a Lunar Evacuation System Assembly. This is a tool for the astronauts because the spacesuits are very heavy and bulky, and the astronauts will have problems despite the reduced gravity, they will have problems with picking up astronauts. So they came up with the idea of this kind of crane and this support cart, which will be able to take the astronauts to the safe harbor. Thank you very much.
Thank you, Matt. Appreciate that. Stephen, if you want to go ahead and load your presentation and
certainly
rock that.
Enable screen sharing, please.
Shoshana is working on that one.
Beautiful. Thank you.
Yeah. There we go.
Hey, everyone. Morning or afternoon or good night, depending on where you are in the sphere. My name is Stephen Dare. I'm a planetary science and technology analog researcher and CEO and founder of Protean Industries. So for the past 3 or 4 years, we've been working on this idea of trying to push robotics and human factors in underwater environments for astronautic analogs. And what that kind of relates to is taking underwater cave environments as a baseline for these analogies and extending them to be able to prepare for lunar and Martian environments. And there are several factors that kind of relate into this idea on where each specific cave is meant for a specific type of research. So where you need isolation, you'll have a deeper cave where you have to hike in several kilometers and then you're just cut off from the outside world for several weeks. Or other caves where there are some open water access where you can just dive right in, no pun intended, and get right to work with a specific scientific tool set. And then we kind of get into the natural factors. So if the cave is developed by water cross-cutting bedrock, or if it's been created from lunar lava tubes. So that kind of gives us this paradigm where we can use water-cut caves to understand what we might experience on Martian environments underground, and lunar lava tubes are what we'd expect to see from skylight caves on the moon that we could hopefully start sending robots in with the Artemis projects. That all being said, a lot of this work in the past decades has all been laboratory-based or extremely controlled environments, and the moon is not a laboratory. We need to start preparing for those real-world aspects of doing science in the wild and not having an immediate safety net to conduct these activities. So we kind of start bridging into the contextual behavioral psychology of the entire situation, and we want to start providing this 5, 4, 3, 2, 1 stop, think, breathe, act scenario into every astronaut's training courses. ESA Caves has started to work in these areas, but there's a lot more to be done. And if we can start bridging those gaps, you can use that in your everyday life as well as in these underwater analogs. From there, we want to start considering the unexplored terrain beneath our feet and what that kind of relates to in terms of missions for the moon and for Mars, where we've only just touched the surface and we really need to start digging in. Ultimately, another objective of today's course is to understand how underwater environments can be utilized for tool development in astronautics and for underwater engineering, and kind of learn who the most isolated human in the world is and what that'll turn into in the coming decades. So I mentioned the 5, 4, 3, 2, 1 concept, and that's within contextual behavioral psychology to kind of get people to overcome claustrophobia, anxiety, and a various myriad of any kind of psychological stressors which could prevent you from completing a task or cause you to freeze up. And as you can kind of see from these videos, these underwater cave environments really stress the human body to the nth degree. You're under hundreds of feet of water, sometimes kilometers deep into a cave where it takes hours to swim back out from where you've gone to work. You're in a pitch black environment, and the the geometry of the environment continuously changes from either being a giant vaulted cavern where there's hundreds of meters between you and the next wall and hundreds of meters below you on a drop off, or tunnels that are just about wide enough where they're half a meter by half a meter and you can wiggle through them. So you kind of want to keep these things in perspective as you're going through to keep yourself safe and keep your teammates safe. And that's you want to keep a perspective on what you can see or can't see, what you can feel, hear, smell, and taste. And that all relates back to how your team is doing and how you can conduct the mission you're on. And then after you've gone through those 5 steps, you want to stop, breathe, think, and act before you move through your next set of tasks to be able to keep the environment in some sort of control around you. And that relates to equipment safety, the depth you're swimming within, if you can actually communicate with your teammate either verbally through written text or just by body language. If you can smell any kind of hazardous chemicals, hydrogen sulfide fills some of these caves from rotting vegetation and organic matter. And if your breathing gas has actually been tainted with any kind of chemical. And then just the salt or fresh water can be a good indication of how far you are from a cave entrance and how deep you are. Circling back, we can kind of see on the top right slide, this is a map I generated with Space Shuttle topography mission data, and it kind of it makes us start to think about this entire unexplored world beneath our feet. And the map below that is a map of all the potential cave systems on Mars. There needs to be a map like this developed in full scale for the moon, and it kind of really puts into perspective what we can see with just a passing satellite observation or with any of the rovers. But what we're really missing is underneath our feet and access to the groundwater table, where we could possibly find signs of past or present life on Mars, where interactions between the water table and chemical elements is likely happening and would draw some kind of evolutionary processes. And this has been an ongoing mission since the early 2000s with the Institute for Advanced Concepts at NASA starting to get a feel for what these subterranean environments are able to be utilized for on Earth to improve operations in space. So we can kind of see on this top left picture what that kind of relates to. You have a team that goes 2 to 5 kilometers into a cave and sets up a campsite. They have access to the water table and can start laying hundreds of kilometers of cave line while they're scuba diving. And they get that ability to kind of have that isolation factor as well as the environmental factors that you'd experience on the moon, where if you kick your fins too hard, you could have an entire silt out. Where you could also have a debris storm or a debris cloud form if you're bouncing around the moon and not paying attention. So the bottom left image and the middle image are actually NASA HiRISE data from Arizona and Arizona University, and some advanced concept studies for possible lunar skylights. And this lunar skylight in the center is actually about 200 meters deep and 300 meters wide. So that kind of puts perspective into what we're going to kind of need to go through and how caves on Earth give this really high fidelity aspect where you'd have to rappel down into this cave before you can even start doing the work. So you've got to push the spacesuits to that level of durability and able to deal with rope work as well as maintaining the life support systems once you get inside the caves. And that all bounces back into using neutral buoyancy, like Matt said, as an analog for microgravity, where you can properly weight people underwater to have a lunar gravity effect and then have them start practicing with the systems. Within scuba diving, you could either have simple or complex life support systems with open circuit systems where you just off gas, or full circuit rebreathers where you actually have to maintain a certain chemical balance to extract the carbon dioxide you're breathing out from the air that you're breathing in. I already mentioned the lunar dust storms compared to cave silt outs, and the analogy is really on point in between those two, and it can really help get a sense of the dynamics of the human body in motion in these environments, and how dangerous things can get if you're not paying attention to your actions. And that funnels back into stop, think, breathe, act. And of course, being able to sample for biological compounds and do cave geology studies gives us a finer insight into what we might expect in lava tubes on Earth compared to the moon, and water-cut caves on Earth compared to Mars. And ultimately, this all turns into a factor within the human element, where you want to have the person operating in a slow manner, and that would ultimately mean they're being as efficient as possible, and the outcome of the mission turns out to be the fastest because there's the least amount of distractions or risk involved that might cause any kind of negative impact. So the LESA projects with ESA and NASA to promote underwater tool testing are kind of a really good paradigm to start thinking about bringing these same examples into a lunar cave environment or a Martian cave environment, which haven't really been assessed yet. As you can see, that tripod is a good 2 to 3 meters tall, and I can tell you in some of these caves that system wouldn't work, so you have to start considering those contingency plans. If you have a team member in a lunar cave or in a Martian cave and you cannot fit that system, what can you do to start performing your wilderness medicine to be able to help them out? Having either a submersible or a teleoperated robotic system may be a good method to be able to start bridging those gaps, and that kind of does relate back to that issue of human-robotic interaction, where humans can think on the fly, use past and present knowledge, and use future intuition for problem solving. Robots can really only operate in a programmed schema for a certain situation. The trade-off being those same robots are able to be constructed to a higher degree of durability, and they can survive in a lot of extreme environments where humans can't. So balancing out those two elements and having them synergize is a pretty massive factor in trying to start to really explore and develop space in terms of the human aspect and the robotic aspects. And that's where cave diving comes back into the equation. So bringing us into these environments, we're able to start training high school students on the baser levels of underwater surveying, underwater 3D scanning, and underwater robotics. So the video on the top left is actually some of our recent training course that we conducted in Florida. And the propensity for the younger generation to pick up these systems and work in a teleoperated setting is pretty impressive. This is one of the 16-year-old girls from our group who's a scientific diver, following myself on a photogrammetry survey of a cave to make sure that if there's any issues, she can communicate that to the team for a safety extraction, or just to be able to cover areas where we might have missed in the survey. Beneath that is an underwater laser scanner, which kind of starts hitting on the cutting edge of being able to cross this boundary where we've just been using the hand mapping techniques of the past century and getting them into this century, which is the photo on the top right that you saw the girl collecting information on that underwater slate. So that kind of brings us into this new paradigm of being able to really push that the human element along with these tele-operated robotic systems to get the most data we can in the most effective means possible, while keeping our teams as safe as possible throughout their missions. And in terms of isolation, it could be said that Al Worden was the most isolated human being of all time, at a total distance of over 350,000 kilometers away from Earth when his team was operating on the moons of on the mountains of the moon. And we kind of can put that into perspective of working in these underwater environments where it may only be 10 or 20 kilometers away from the exit, but then you're another 50 kilometers drive away from the nearest hospital, and you've kind of got to start working in those scale factors of what you can bring with you, what you can't bring with you, and how you would prepare for any emergency situations. So my challenge questions for the day are, what are your ways of being self-sufficient? How can you see using 5, 4, 3, 2, 1, stop, breathe, think, act in your everyday life, and how can you use those centering techniques, or what are your centering techniques that you can use aside from those two focuses?
Great. Thank you, Stephen. That was awesome. I'm going to introduce our panelists real quick, and then I'm going to introduce a few questions real fast. So we've got Shauna Pandya on our panel, Kyle Foster, Jason Remuller, and Ken Trujillo. And so real quick, I wanted to start with a question probably directed at Matt, but anybody can help out. But Matt, you mentioned having pressurized gases as an aquanaut. I don't know if you're not a diver, I don't know if a lot of people understand, what that means. But then also, how does that apply when you're in space, in like a pressurized spacesuit?
So I'm personally a dive master, so I'm on my way to being a dive instructor. So when you are underwater, there's a different feeling you get from the environment. You have to be self-sufficient, and you have to keep yourself to the point when you have to restrain yourself. So I remember one situation we calculated with that was on the deep diving course. We were down, like we were 60 meters down, and I calculated that the air will be enough and will be sufficient for my dive. But our dive didn't start like we planned. So we started from going down, then my partner had some problems with the ears, so we emerged, and then we dived once again. And we didn't hit the exact point when we wanted, but we did a little bit from the away, and then we have to swim to that point of our interest. But during that time, and especially if you're very deep down, you have different performance of your air. So the air is losing, you are losing your air very quickly. And then I checked on my gauge, and I realized that I am not able to emerge to the surface. I cannot. And most of the people probably in this situation will panic. But we talked about this situation before with my partner. We calculated all the things. I was aware how much air I will have, and that I'm on the margin, but we have safe margin, and that's okay. But during this descent and ascent, we lost this air, but I knew that I have my partner and I can count on him. And he knew what we have to do. So I swim to him. I showed that I'm out of air. He prepared the breathing device, and he had 2 bottles, and we were able to breathe with his devices, and we will slowly emerge. And this situation show how you can train people underwater when the consequences are hard to imagine. If I emerge the 60 meters, you cannot swim 60 meters. Okay, even with the expanding gases in your lungs, you cannot go ascend. You have to rely on your partner, you have to trust him, and you have to have all the things thought through before. Otherwise, you die. And this is I think, the best analog that you can have.
Yeah, that makes sense. So for our panelists, I'll throw it up for who wants to grab it. What are some risks that you encounter as an aquanaut that you don't encounter in space?
Sorry, Anthony, was the question, what are the risks of an underwater animal and how do they tie into space?
Yeah, as an aquanaut, what risk might you encounter that you would not see in space?
Oh,
That's a really good one. Being underwater as the first one, instead of having an air seal blow out into space, you'd expect where an air seal might blow out on a spacesuit, an air seal blowing out in a dry suit mean you'll have a pretty wet day. um, that would be the first one I would notice. The second one would be um, inertia and flow, where in outer space you don't have anything to really resist against, and if you push your hand off something, you'll float away pretty far. The water is pretty good at preventing that, and you also wouldn't have flow underwater, or you'd have flow underwater where you wouldn't have it in outer space. So in some of these cave situations, you've got to plan for a 2 to 3 knot current pushing you either farther into the cave or pushing you back towards your exit. So you've kind of got to plan out by rules of thirds, which means you breathe a third of your air tank going in, or you use a third of your closed circuit rebreather gas going in, and then you use a third to get out and keep a third for emergencies. You wouldn't have that issue as much in outer space because you aren't actively swimming against the water flow, either going in the wrong direction or the same direction as you.
Just to add to that, Anthony, that's a great question, and just thanks for that, Stephen. I think the biggest thing is also looking at depth and if you're in saturation or not. So, for example, Kyle and I were at the Jules Undersea Lodge on a 5-day underwater mission, but we were at 21 feet. So we did brief contingencies. As Matt said, it's so important to know what is your plan B, C, D if things go sideways. And our plan, because there was no decompression time, is that we could get out of the danger zone and swim to the surface, which was, psychologically, nice to have that safety net. Whereas at the Aquarius Reef Base, where they run the Nemo missions that Matt was talking about, I had the opportunity to stay there once overnight. We were at 1 atmosphere pressure, but when you're actually there on a mission, you're in saturation. And if you're there for over 24 hours, you cannot leave immediately because you have to decompress. And the decompression time is 15 hours and 47 minutes. So if there's a fire in the HAB, then you have to weigh the risk benefit of do I leave immediately and risk a dive injury and an air embolism that could kill me, or is there anywhere else I could go? So even on the ISS, the second you push the red button to get off the X, get out of that danger zone, and pull the trigger to evacuate, get into your Soyuz or whatever capsule you're using, and land in Kazakhstan, that's 3.5 hours. You can immediately leave the environment. At Aquarius Reef Base, you cannot, or if you do, you have to accept that the danger that faces you currently better be such that it justifies the risk of accepting an air embolism or a dive injury. So that would be one of the biggest lessons or the biggest risks and differences from a medical standpoint.
If I may add 2 things. The first thing is wildlife. You don't have wildlife in space, at least we don't know about it. So for sure you will not see sharks or something like that. That's the first thing. And the second thing, exactly what like you mentioned, and even if you have a partner, so every technical diver knows that, every technical diver knows that you are on your own, okay? So when you are diving deep down, you cannot, so for example, if I'm out of air, he can share the air with me, but he's not obligated to. And I can die because I made some stupid mistakes. And on this space, I think it's a bit better because the astronauts are helping each other and so on. And you are not in such extreme condition, and you have your EVA suit which can withstand even with the punctures, like for half an hour or so. You have suit which can withstand for 8 hours in the vacuum. But Luca Parmitano was almost dead by drowning in space. So yes, you can also drown in space.
That is an interesting point. Yeah, that can happen, or it did happen once. I also, in regards to that, for cave diving, you always keep a redundant system with you. So if you get into that situation Matt was talking about, you have 2 isolated life support systems, whether that be rebreathers or scuba tanks. So you kind of plan for the worst and hope for the best. And there's also one or two other critical rules, which is any team member that calls a dive, there's no discussion. The cave dive is canceled or the technical dive is canceled, and you immediately head to the surface to prevent any injuries or problems. But you do take that risk into consideration of what is the glass ceiling that you can't go through if you're looking at a depth limit or a pressure limit or an air limit. You kind of want to always keep that in the back of your mind. Within rescue diving, there is also a concept where if someone breaks the limits, you can only do so much to help save them if they do. And if you can't save them, you have to do what you can to get back to the surface and call for help to go and find them. So it's not a perfect system, and that's where, yeah, we've got this tool use and development with LESA and these other areas are really critical, especially when you start getting into those environments where the human body was not conditioned for.
Great. And kind of to flip that around, where do you think the limitations for aquanaut or water training are for training to go to space? Kyle, we'll throw it over to you.
I think they go hand in hand with a lot of the benefits that Stephen indicated of doing the underwater training. You end up with considerations about flow. If you are doing EVA, like spacewalk, extravehicular activity training underwater, there's a lot of considerations that need to happen there in order to deal with the actual environment that you're working in. So you have buoyancy bags. If you're in a spacesuit underwater working on a model of the ISS, you've got buoyancy bags and support divers there who are helping you train. They do their best to stay out of the way. But you're still in a 1G environment. So you may actually be upside down, but you may be upside down and your head is in the top of your spacesuit because you're not actually in microgravity. So there's limitations in how far you can go with simulation. It's good for simulating the gross mechanics of operating in an airless environment. But some of the trade-offs to get there, I'm not sure they'd constitute negative training, but they are definitely considerations that you need to be cognizant of when you're doing such things.
I'll add
Just
a little bit.
Yeah. Oh, sorry, Jason, were you saying something?
Sure, I was going to add a little bit to that from a perspective of a possum, or in particular otter. That's our EVA spacesuit program.
Jason, can you turn up your volume?
Certainly. How's this?
Yeah, much better.
Okay, thank you. So everyone that comes into our program has a background in scuba diving. And at first, that's honestly a claustrophobia check. We don't want people freaking out the first time they get in a spacesuit. When we look at qualifying something like an EVA spacesuit, you have to demonstrate that it's going to behave in the environment in which it's designed. It's very hard to do. You can build something that works in a laboratory, what we call a technology readiness level of 4, and how do we actually demonstrate that we can take this to space and it's going to function in space, meaning we can elevate it to a TRL of 6 and then to 7. And that's like a whole lot of different analogs, and different things provide different ways that we can recreate that analog. So right now, our first step was to do a mechanical system called a gravity offset system. It's a mechanical system that can simulate different levels of gravity, but you're still always in 1G. Our next step as a program is to look at underwater EVA. We are hopeful of doing that next year. So the question is, what does this add? Well, one, you can do all axes of movement. You can translate across long distances. Where the gravity offset system is a 2-axis system, you can simulate 0G up and down, and you can move along one axis like you're walking on the moon. But when you're actually evaluating a suit around a representation of, say, a space station module, that's a whole different, you need more axes of freedom, you need to rotate all sorts of ways, translate yourself, and do it for a long period of time. Now, the third way we're going to look at this is an extension of what we've done now for 5 years, and Shauna knows very well, is microgravity testing in a parabolic aircraft. Now, this actually does create a true sense of zero G. The most possum students, have they come in, we show a film called The Spacewalker. It's about Alexei Leonov's first spacewalk, and there's a great scene in there. They're first testing their very first EVA spacesuit in the, I think it's an Antonov, it's a parabolic aircraft, and you get about 25 seconds, and they're trying to show that the cosmonaut could actually get inside of that airlock. So, but you're limited in time there, and it's an expensive way of doing things for a small bit of time. So every bit of this provides a little bit of piece to the puzzle, how we can create these analog environments to evaluate the suits, to develop training of routines that we can provide the suit wear, but also, and Matt, you alluded to this earlier, or you talked about this earlier, is tools and techniques. How the suit's only as good as what it can enable in terms of science and research with the human in the loop. So our philosophy as a program is to have preparatory courses. One coming up now is for underwater, but we've had Shauna's operational space medicine, and then we have a planetary geology course, and that the students are challenged to develop tools and procedures that then we can take in these analog environments like the gravity offset and like underwater. So that's kind of in a nutshell of how underwater environments like this, you have the penalty of having the buoyant force, but you do have the benefit of being able to operate in all axes and through much longer periods of time.
So yeah, just to add to that, I think that was a really, really good overview, Jason. I think when you look at the trade-offs between analog environments, and so the reason we call them analog environments is that they're analogous to some facet of space. And so there's no 100% high fidelity replica of space here on Earth. And so then we look at all these different environments to replicate some aspect of a spaceflight environment, because it's incredibly high risk, it's incredibly expensive to give us that extra buffer of training, that extra layer of training. So the water world gives us that isolation, it gives us that self-containedness, it gives that element of risk. And there's also that element of we truly are alone, because even if we're on Earth, even if we don't have micro or reduced gravity, if in a place like Aquarius Reef Base, you do have that 16-hour decompression time. As Jason said, in the microgravity flight, you get to replicate the zero G or the microgravity. On an analog environment, say at the Mars Desert Research Station, high seas, Lunaris, you make the simulation as high fidelity as you put into it. And so if you respect that you truly are on Mars or the moon, then you're dressing up every single time you go outside for an extravehicular activity because you're in your life support system. So all of these analog environments have so many lessons in one facet or another, whether it's gravity, whether it's isolation, whether it's self-containment, whether it's being at home in isolation during a pandemic, that have lessons that learn that we can actually apply to our future endeavors going forward.
Thanks, Shauna. That was great, Shauna. To kind of start tying up the panel, we're obviously doing a lot of this because of the COVID-19 pandemic. And so from what you've learned as an aquanaut, does each of you have like one tip that you can apply to the current situation? Shauna, we can start with you.
Sure. Yeah, I was just engrossed because I saw Kyle smiling and nodding. So I was curious to hear what he said. So there's so many lessons, but I think the number one is know your team, and realize that you're a crew. Build your crew. Rely on your team. Ask how you can build them up. Ask what let them know how to intelligence to let them know how they can help you. So realize that even if you're in isolation, you're not alone. Rely on your crew, but also express that and be productive about how you approach it.
Yeah.
So I'll follow.
Oh, I'll let you
ahead.
go, Kyle. Oh, no, you're good. You go take it.
Thanks. I was going to say to add on to that, manage your logistics chain. When it comes to working underwater, there is so much that goes into preparing for a dive. You need to have all your equipment ready. It needs to be in good operating condition. You need to have the appropriate consumables, whether that's air or nitrox or what have you. You need to have your transportation worked out. If you're going to be living underwater and being an aquanaut, you need to have your food situation squared away. One thing that I learned from our first officer on the Neptune mission, Paul, he is a world-class logistician. He had all this stuff locked down and on a timetable, and he knew exactly what was going to be where when. It's very, very similar to, okay, do I have enough groceries so that I can stay in without needing to go to the store every day? Do I have like 1 or 2 weeks worth of food? I'll make the joke, do I have enough toilet paper? Stuff like that. Gets a little soggy underwater, but you make do. So for me, I think the big takeaway is knowing your logistics.
Great.
For
And
me, one of the
oh, go ahead.
okay, go ahead.
No, go right ahead.
Okay, so for me, very quick. One of the takeaways is that you can do fun stuff and really educational stuff during the isolation. One thing about looking at the isolation is like boring, but then you can see and do stuff which you cannot do on the everyday basis. And I use that stuff a lot. And to be honest, I even more busy than on the normal days. So I'm really maybe not glad that we have this kind of situation, but I'm happy that I was able to find how to use this time in the proper way. So isolation is not also a bad thing. So you can use it for good.
I'd just like to add one more thing to that, is that deep diving and cave diving are a really good analog for astronautics, because they're environments that you can't instantly disassociate from. You know, there are ways you can provide for genuine mitigatable risk, but the genuine mitigatable risk that is in an environment that you can't just disengage from. So when you're flying a plane, or when you're climbing a mountain, or when you are deep diving or cave diving, simply going to the surface is not an option, and you have to rationalize and think through these things. And what the whole planet is forced to deal with this now, is that there is a threat, and that we don't know much about the threat, and all these things that the panel has talked about in terms of logistical planning, communication, what is your network, your quarantine family, and your systems of support that are going to get through this, and that same kind of thinking and training will benefit.
Yeah, great. Thank you, Jason. And thank you all of our panelists and our keynotes. We're at our time, so I'm going to hand it back over to Shauna and Shayla.
Great. That was so wonderful. Thank you so much for moderating, Anthony. Thank you, Matt and Stephen, for your excellent lessons learned. Really loved hearing about the 5, 4, 3, 2, 1, stop, breathe, stop, think, breathe, act. Sorry, breathe, think, stop, act. Got the order wrong, but we will send out that summary. And thank you very much for all of our panelists for sharing your experiences and your lessons learned. So I know there were some really good questions about book recommendations from the panelists, as well as has aquanautic experience ever been undertaken in Antarctica? We will answer those at the start of Monday's webinar, which Shayla, I'm going to turn it over to you to introduce.
Yes, and of course, Sean already said it. Thank you. Can't thank you enough, participants and panelists, and definitely thank you. Big thank you to Shauna, because she's been doing a lot of the work, putting everything together, and making sure this is a seamless webinar. So definitely join us tomorrow for No Human is an Island, but Life Support Systems Should Come Close, where you have a lot of our panelists that have come in the previous webinars, and this is Team Possum signing out.